Hello everybody. Well, a few weeks ago I asked for your questions and I got a whole bunch of them, and in fact I had to split them up into 3 videos. So this is part 2, and today we are going to look at, is it true that only electrons move to carry electricity? And if glass is made of atoms, how come we can see through it? And why can't we see through walls then? Okay, next question. My teacher told me only electrons can move. So how come you can have positive lightning strikes? What are they made of? This is a great question. I have really been thinking about this all weekend. Let's talk about a couple of things first. First of all, there's 2 kinds of lightning strikes. There is the most common negative charged lightning strike, and there is the rarer and more powerful positively charged lightning strike. If you want to see a great video on them, check out the banner, it'll be here, all right? Check out the link. It is fantastic video. But the question is, I mean, electricity is made of electrons, right? Everybody knows that. So what is going on here? Well, I think the first thing we have to look at is the idea of, is it really only electrons that move? You will certainly see that said a lot, and especially in discussions of electric charge, you will see a lot of physicists saying that it's the electrons that move. And the reason for that is very simple. When we have an atom, you have your negatively charged electrons and you have your positively charged nucleus. And the positive charges come from protons inside the nucleus. Well, a proton has about 2,000 times the mass of an electron. So to give you an idea of what that would be like my mass versus the mass of a large Navy patrol boat. Let's imagine a situation. Let's imagine I'm out on the sea and there's a rope between me and this big patrol boat. Let's imagine that I'm on a little inflatable dinghy. So I pull on the rope. What's going to happen? Well, obviously I'm going to pull myself towards that big ship. All right. Now, in reality, I'm also pulling the ship towards me. But anybody watching will see me moving along like this and the patrol boat moving like this. Okay. Sure, the patrol boat is also moving, but it's barely moving. So, for all intents and purposes, we can just say it's me moving. It's me pulling myself to the boat. We can forget that the boat is also moving because it moves such a tiny distance. And this is where the idea that only electrons move, because they are 2,000 times lighter than protons in the center of an atom. If you've got enough energy to move a proton, enough kinetic energy to move a proton, then you have got enough kinetic energy to move 2,000 electrons. So there really isn't much point in worrying about positive charges moving. Rather, you can just think about the electron negative charges moving. And that's all fine. Except that the big patrol boat does move. It might not move very much, but it does move, and it can move, especially if you give it enough energy. So what's that got to do with our positive lightning strikes? Well, this is really interesting because really this is physics. And here I have to admit, hey, I'm a chemist, all right? And chemists explaining physics is about as good as physicists explaining chemistry, all right? They do what they do and we do what we do. But here's my take. What's really interesting about lightning strikes is that nobody really understands them. The first thing they don't understand is how we get this charge separation in thunderclouds. If you go and watch any video about how lightning works, and the video, the link that I posted is a classic example, they will tell you that in a thundercloud, they'll tell you that the positive charges and negative charges get separated. Often they will tell you that's because of friction. But nobody really knows how that happens. And then, because of this positive charge, this charge separation, we get our lightning strikes. If the strike comes from a negatively charged part of the cloud, we get a negative strike of mostly electrons coming from the negative part of the cloud down to the Earth. If we get the lightning strike coming from the positive part of the cloud, then we get this positively charged strike coming down from the cloud to the ground. It's a bit more complicated than that, you'll see in the video, but let's stay there for now. The problem is, what's happening with that positive lightning strike? If these protons, if these nuclei are too heavy to move, how can we have a positively charged lightning strike? Well, there's two ways of looking at it. There's the physics way and there's the Robertson way. Now, the Robertson way, I have to say, is just a hypothesis. And once again, hey, I'm a chemist, but let's come back to it in a minute. The physics way is to say, well, okay, it is electrons moving. But what's happening is that electrons near that positive part of the cloud way up the top are being pulled into that positive cloud. That leaves behind a positive charge. That positive charge then pulls up more electrons from underneath it. That positive charge then pulls up more electrons from underneath it. That positive charge pulls up more electrons from underneath it until it gets all the way to the ground. So what's actually happening here is that electrons are being moved, and the electrons moving from the top of near the top of the cloud leave a positively charged path, and that ends up being the same thing as a positive lightning strike coming down to the ground. That's how physicists will explain it. I think there is at least a possibility that things are not quite like that. The first big problem we have, remember that charge separation and how we don't know how it is that friction or whatever inside a thundercloud creates this big patch of positive charge and a big patch of negative charge. We don't know how it happens, and we can't recreate it in a laboratory. Of course, we can make really big electric sparks, but these are big sparks that go between metal electrodes, and we can kind of make a lightning bolt that goes through air, but it takes a lot more energy to do it in a laboratory than it takes in a real thunderstorm. So the question is, what's going on? And one big possible difference, of course, is dust. There's going to be a lot of dust inside a thunderstorm, and it's going to be very wet. And that dust is carrying with it lots of ionic salts. So we have lots of physical ions up there, both positively charged and negatively charged in the cloud anyway. But there's another source of positive charge, which I think is maybe more important. Now, we're going to look at water. Now, we know that water is H2O. But if we add some acid to the water, we can get hydrogen atoms breaking away from the acid molecules in the form of hydrogen ions, which are actually protons. These are particles that carry positive charge. So once we have this acidic water, we have these extra positively charged protons moving through the water quite freely in the form of H3O+. That's basically what acid in water is. If we've got this dust rising up into the cloud, and especially if it's organic dust, the kind of thing you find from soil, those raindrops can become fairly acidic fairly quickly. And that means we have got a source of freely moving protons. Now, they can't move as quickly as electrons can, but they are moving around. So, could these protons be somehow getting separated within the cloud? Certainly part of how the charge separation occurs is by a mixing stage where we have this really supercooled liquid water mixing with ice crystals. And this seems to me a point where we could really be concentrating out these protons. And if we have a lot of them in one place, we could be getting a large concentration of positive charge. What's the next point? Well, again, I don't know what the exact energies of this situation is, but the positive lightning strikes are much higher energy than negative lightning strikes. The explanation in the video that I linked to is that happens because the positive area of the cloud is so much higher and further from the ground. So you need a lot more energy before it can make a spark. Fine. But if our spark is formed of protons rather than electrons, then those protons are going to have 2,000 times the kinetic energy of the electrons. And that could be what makes these positive lightning strikes so damaging. I couldn't find any properly written examples of information online that really made it clear that these positive strikes were definitely a case of electrons moving up rather than positive ions moving down. It was the kind of thing that people kind of said in an offhand way, but they didn't really make any definite analysis to back it up. There should be ways that people could check the lightning and see what is actually moving through there. The problem is that we have very high energy plasma now. We are literally stripping electrons away from atoms to the point where we don't really have separate atoms anymore. We just have nuclei and we have electrons all moving around like crazy. That's kind of an argument against my chemistry idea because the rules of chemistry break down inside a plasma. But at the same time, it makes it difficult to analyze that lightning strike and see what is actually inside it. So, quick answer, most likely it is occurring because electrons are moving from the top towards the top of the cloud, and they make a path that other electrons follow and leave behind them atoms which have been stripped of their negative electrons, which is the same thing as a positive path coming down. But I think there is a possibility of generating a very high concentration of positively charged protons at the top of the cloud. And I think there is a possibility it's the protons coming down, which would explain why positive lightning strikes are rare and high energy. Next question. If glass is made of atoms, how come we can still see through it? Why can't we see through walls then? Well, there are two reasons that we can't see through things. The first reason is because light gets absorbed. In other words, something has a color. And if it has enough color or the right mixture of colors, then it's black and you can't see through it at all. Think, for example, sunglasses. If you have one pair of sunglasses, you can see through them okay, but if you line 10 pairs of sunglasses in a row, they'll go black and you can't see through them at all. I'm not going to talk about that because that's not the difference between glass and walls. So let's talk about windows and walls. What is the big difference between walls and windows then? Well, it's not atoms, it's surfaces. You see, what's special about glasses, and I'm going to say glasses here because there are many different kinds of glass, but what's special about them is that you can melt them and solidify them, and they stay in the shape that you made them. That's what's special about them. And in fact, the reason they're special is that they must have at least 3 ingredients in them, at least 3 different elements to make a glass. And what that does is it stops the atoms from making crystals. So glass is not made from crystals, but glass is a solid. Okay, we are often told that glass or glasses are liquids, and that's not true. Glasses are a solid, but they're a special solid which hasn't formed a crystal. So what's the big deal with crystals? Well, if we take most solid compounds, as they form the solid, they will form themselves into crystals. We have an definite arrangement of these atoms, every atom in its exact place in the crystal. Now, the interesting thing about individual crystals is that they are clear. You can see right through them. Even if you take a crystal of something that we normally think of as white, for example, sodium chloride or table salt, or for example, table sugar. We think of them as being white powders, but actually they are just lots and lots of very small, clear crystals. In fact, I might even have grown you some crystals for this video. Did I do that? So, if a crystal is clear, why does sugar and salt look white and why can't we see through it? And the answer is because they have surfaces. You might already know that when light goes through something like water, it changes its direction. Okay, we say it is refracted. So if the light hits the surface of some water, the light changes its direction, comes out the other side, and it changes its direction one more time. And the same thing happens when light hits the surface of a crystal. So what does that mean for us? Well, the first point is that if we change the direction of light many, many times, any particular piece of light coming from one direction is going to be scattered around inside those crystals. It's going to be refracted and reflected from the inside surface of the crystal and from the outside surface of other crystals. So the light is going to be bounced around inside and all mixed up together, and that gives us white light. And we will also have a prism effect, so that the light will actually split up and break up into its different colors. But that's happening all the way through our powder. So it's all getting mixed up again and giving us white light. So as the light goes into our powder, it's reflected off many surfaces and eventually gets reflected so much it comes back out again. And that's actually what's happening in our walls. Another thing that causes extra surfaces inside the material are tiny microscopic air bubbles. And that's what often happens inside ceramics. Here I have a piece of broken cup, I don't know if this is going to focus on that. There we go. And just in there you can see the rough surface of the ceramic. And that surface is made of microscopic crystals and microscopic air bubbles. Now what makes it shiny on the outside is that there is a glaze on it, which is like a kind of glass. It's brown because we also have a color in there which is absorbing some of the white light. But that glass-like glaze on the outside makes a smooth surface with no air bubbles and no crystals. And that means the light can go right through for a tiny fraction of a millimeter, maybe just a few micrometers. But that makes it shiny. So you get a reflection from the outside of the glaze. But any light that goes through the glaze gets bounced back again by those tiny crystals and air bubbles inside the ceramic itself. So the reason that we can see through windows and not walls is because glass can form a solid, a smooth solid, which doesn't have any surfaces, doesn't have any crystals inside. But when we make a wall, we make tiny crystals, and those crystals bounce the light back out again. Well, thank you for your questions. If you found that interesting, why not check out part 1 and keep an eye out for part 3 when that comes out. If you like this video, I'll make more, and if you subscribe, you'll know when the next ones come out. And if you write any questions or thoughts or comments, I'll get back to you as soon as I can. See you next time.